I'm very glad to speak here. Thank you very much for the introduction. And it's, of course, a great pleasure to be at this place in this very nice conference with many different topics. Today I will speak about a topic which has not been addressed so far during this conference, namely spinor geometry and applications to differential geometry and topics beyond differential geometry, maybe. So the title is called Lipschitz rigidity for scalar curvature. And let me start with a baby case to set the stage what I will be talking about. So the talk will be about scalar curvature and spherical comparison. So we study the round sphere from the perspective of comparison geometry using spinorial methods. And throughout the talk, Sn with this double bar here will be the round unit sphere in dimension n, and the scalar curvature of this sphere is n times n minus 1. Now let's look at two-dimensional sphere. So this is a very easy example, but we can see very important principles that will be then generalized to higher dimensions. Namely, if you take any Riemannian metric, smooth Riemannian metric on S2, different from G0 or maybe even equal to G0, and we assume the two following properties. Namely, we have a scalar curvature comparison and we have a volume comparison. So the scalar curvature comparison says that the scalar curvature of G, or if you wish, the sectional curvature, is bounded below by the scalar curvature of the round sphere, and the metric G is bounded below by the metric G0. So the lengths of G and G0 can be compared in this way. And then, under these assumptions, the two metrics must be equal. Why is that? So the point is that we can write down this integral, and we know that this integral does not depend on the metric G. So we integrate the scalar curvature, which is a real valued function, and this is the volume element associated to G. And now if you take G0 instead, then these two integrals are equal. So this we all, of course, know because this is a topological invariant, but we need not actually know what topological invariant it is. It's enough to know that these two integrals are equal. And now if we have both these inequalities here, so this integrand is larger than or equal to this one, and the volume form is larger than or equal to the volume form here, this means using that the metrics are actually compared in this way, that the metrics must be equal. G equals G0. And this indicates that somehow these two quantities here work against each other. You cannot increase both the scalar curvature and the metric at the same time, unless the metrics are already equal. So there is no possibility as here. So it's really a rigidity statement in this respect. And now let's look at higher dimensions. This is a famous theorem of Llarull from 1998. And this is a far-reaching generalization of the fact that I indicated on the previous slide to higher dimensions. We take a closed smooth connected manifold M of dimension n at least 2, and we assume that the manifold admits a spin structure. This means that the first and the second Stiefel-Whitney classes vanish, or the manifold is orientable and the second Stiefel-Whitney class vanishes. And again, I have the scalar curvature comparison to the scalar curvature of the round sphere. And now there is some new ingredient. The manifold M can be different from the sphere. It can be any closed smooth manifold. But instead, we compare M with Sn by a comparison map F, which we assume to be smooth and of degree non-zero. And now, on the previous slide, I assumed that the two metrics can be compared to each other. This would correspond to the fact that the differential of f, the norm of the differential is bounded above by 1, so the map is 1 Lipschitz. but actually in dimensions larger or equal than 3, it is enough to assume that the norm of 2 vectors is not increased by the differential of f. So this thing here measures the stretch of areas of infinitesimal surfaces under the map f. So this is a weaker condition than this one, but in dimension 2 we need this condition. And then f is a Riemannian isometry. So this is quite remarkable. It's actually sort of unheard of, I would say, because this is the round sphere here, and then this manifold M can be anything, any metric, and I mean we know almost nothing about it apart from these rather weak conditions. So scalar curvature is a rather weak curvature condition, and then we have this comparison map F whose differential satisfies some norm, and then this M has to be the sphere actually, and the map F is an isometry already. This is quite remarkable, and so this theorem has been the starting point for many developments in scalar curvature geometry and also recent ones. In particular, Misha Gromov asked in his 4 lectures on scalar curvature from 2021 whether we can weaken some of these conditions, in particular the map F, this comparison map F, which is assumed to be smooth here. So it would make sense to formulate this theorem by just assuming that F is a Lipschitz map, for example. This is already enough to compare lengths. And also the metric G, which is assumed to be smooth here, maybe it is feasible, it is possible that we can work under lower regularity conditions for the metric G. And this is the theme of my talk today. I will show you how these 2 quantities can be assumed to be less regular than being smooth. Let's start with the metric G, the Riemannian metric G. So if the metric G is of regularity C2, then we define the scalar curvature of G in the usual way by taking second derivatives of the metric and combining them according to the usual formula. And if we want to go below regularity C2, we have to do something different. And this is a notion which is introduced by Lee-LeFloch in a paper by 2015. Namely, they introduced this notion of scalar curvature distribution. The idea is rather easy to explain. If you start on a coordinate neighborhood of your Riemannian manifold and you write down the scalar curvature on this coordinate neighborhood, then it turns out that it is a sum of 2 quantities. This one here is quadratic in the first derivatives of G, and V, these quantities are linear in the first derivatives of G, and then we take another partial derivative in dimension K, in direction K. And now if you integrate this quantity against a smooth function defined on U with compact support, like this, then you can apply integration by parts and put this differential here on the other side, namely in front of the function U. And it turns out that this quantity here makes sense for metrics G which are of regularity less than C2. Namely, actually it turns out it's enough to assume that the metric is of regularity, of Sobolev regularity 1, 2, and continuous, so that we have bounded inverses. But for my talk, it's actually enough to assume, so I will concentrate on the case where the metric is of regularity 1p, and p is larger than n. So in particular, the metric G is continuous by assumption, the Sobolev embedding theorem. Okay, so, but this is definitely of regularity below C2. at the price that we have to pass to a scalar curvature distribution. So the scalar curvature is no longer a function on our manifold, but it's a distribution. But this is actually enough for our purpose. So this is the first ingredient, scalar curvature distribution. And now, once we have introduced this notion, I can formulate the first main theorem, which I proved together with Simone Cecchini and Thomas Schick a couple of years ago. And then we have a new ingredient or a new aspect where also Schönlinner participated. Namely, so we have, again, a closed smooth connected spin manifold of dimension at least 2. And now we assume that G is a Riemannian metric of this lower regularity, as I explained to you before, with scalar curvature distribution bounded below by n times n minus 1. And as a comparison map, I take a Lipschitz continuous map of degree non-zero. It makes sense. It's a continuous map. And now, remember, I had this condition on the norm of the what happens with two vectors in the tangent space. And now the point is that the differential of f need not be everywhere defined, but it's almost everywhere defined because we have a Lipschitz continuous map. So we can measure the two norm of vectors at least almost everywhere. And the assumption is that almost everywhere I still have this condition. In dimension 2, I need the stronger condition that the map is actually one Lipschitz. And then f is a metric isometry. It need not be a smooth Riemannian isometry, but it's a metric isometry. This is the conclusion here. And in some way, this maybe isolates a little bit more than the original formulation of the Llarull theorem, the metric content of the theorem here. So we have a Lipschitz continuous comparison map, and we have a low regularity metric. So what are the main steps in order to prove such a result? The first point, or the first step, proves that the differential of f is an isometry almost everywhere. And for this, we generalize the classical Llarull proof appropriately using spin geometry. And the second step is proving that f is a homeomorphism, and then this condition here follows. And now there is an important point that will be also be discussed later. If f is smooth and df is an isometry almost everywhere, then df is invertible almost everywhere, so everywhere because it's continuous. And then we can apply the inverse function theorem to conclude that the map from M to the sphere is a covering map, and then we are actually finished. So in the usual situation, or the classical situation of Llarull, the second point does not appear, so it's not important. After the first point, one is already done. But if f is just Lipschitz, we do not have such an inverse function theorem, and so we need a new ingredient. And this will actually be the main novel point of this discussion here. I would like to mention that there is a different approach to this generalization of the classical Llarull theorem, namely by Lee and Tam. So they used harmonic map heat flow and the Ricci flow to pass from this singular situation to a regular smooth situation to which the original Llarull theorem can be applied. So this is really conceptually a completely different approach to prove this generalization of the classical Llarull theorem, but in my talk I will concentrate on the spinorial approach. And I think it's still a quite important topic for the future to understand better how these two approaches are related to each other. And maybe from a conceptual point of view, the main difference is the following. Lee Tam reduced the situation to the situation that we already understand very well, to the smooth situation, immediately. So this flow after a nanosecond smoothes out every data. And in this situation here, we really deal with singular objects, namely with this non-regular matrix and with the Lipschitz map F, and try to adapt our techniques to this singular situation so that we can directly deal with it. So this is a little bit a different point of view, I would say. Okay, so the first point is kind of more or less the classical Llarull approach, and so I will recall how this works. And since there hasn't been any talk about spin geometry yet, unless I missed it, maybe not, I will give you a very brief introduction to the main ideas here. So the point is the following. We write down a second order differential operator, the Laplace operator, as a classical differential operator that we all know. And then the question is there a first order differential operator whose square is the Laplace operator? So this is the non-negative Laplace operator with a minus sign. And so actually the motivation to look for such an operator comes from physics, namely from the attempt to combine quantum theory with gravity or with relativity theory. So this is really motivated by a physical problem to look for a first order operator whose square is the Laplace operator. And now we are back to mathematics. So this is a mathematical problem, and Dirac understood that it's not possible to do this for real valued functions, but it is possible to resolve this problem if you look at functions with values in Rn, where this n is a large n compared to the small n here, so it's different. And if we now look at smooth functions on Rn with values in R big N, then if we choose n appropriately, you will find matrices J1 up to J little n, orthogonal matrices, orientation preserving, with the two following properties, namely the square of each matrix is -1 and the matrix is anti-commute. So these are exactly the Clifford relations, and put in more smooth terms, this means that J1 up to Jn span a Clifford algebra. And these actually define a Clifford representation on n-dimensional Euclidean space. So these objects always exist. It's rather easy to define them. And then we can write down a new differential operator of first order where you take the partial derivative in the kth direction. And so this takes a smooth function, and we obtain a smooth function applying this operator, but then we apply this operator, this linear operator jk, going from Rn to Rn. And writing down this operator, we get a first order differential operator, which is called the Dirac operator. And the square of this operator is actually exactly delta. This is an easy, almost trivial calculation using these two relations here. And so this problem is solved. And now one can refine the notions and the machinery to generalize this construction to Riemannian manifolds. And in order to write down or to define these operators, the manifold has to be spin. This is exactly the condition that we can have these operators J1 up to Jn acting on suitable bundles on the manifold M. And so in this case, so just take a smooth manifold with smooth Riemannian metric G. Then the Dirac operator takes smooth functions on M with values in some bundle over M. In this case, it's a Hermitian complex vector bundle, which is acted upon by the Clifford algebra bundle of M. And we get a first order operator, which is locally defined exactly in the same way as we've written down here, just replacing the partial derivatives by covariant derivatives. That's the only difference. And okay, interesting. And now something really remarkable happens. remember that originally we wanted to solve the problem that we have a first order operator who squares delta. And now in the curved situation, we can solve the same problem, kind of, because when you now take the square of this operator that you define in exactly the same way, then an additional term appears when you square the Dirac operator, namely it's the Laplace operator associated to G plus a term which is related to the curvature of G. I mean, this is not very surprising since, as I mentioned, the partial derivatives are replaced by covariant derivatives, and so some curvature terms appear. And this is exactly the scalar curvature, and this is actually, this formula, this is the mother of all formulas, or the whole machinery, the whole method that connects the spin geometry with the scalar curvature geometry. It's this formula here with the scalar curvature term appearing. And now let's make a small historic excursion, namely, where did this Schrödinger equation or this equation appear first? So this is a paper from 32 from, so it's called the Dirac electron and gravitational field, and Schrödinger writes down exactly the same formula. So we have a different sign here. This is due to sign conventions, which are a little different. But on the right-hand side are the eigenvalues squared of the Dirac operator. On the left-hand side, we have the Laplace operator, and we have this additional term here, which involves the scalar curvature. And actually, Schrödinger asks in his paper that, okay, so he says the second summand here should be, or seems to be, of significant theoretical interest, but he doesn't give a theoretical interpretation for this term here. But it appears already, this is really remarkable because Schrödinger did this computation without the very nicely developed machinery of principal bundles and spin geometry that we are used to today. And so he does this in local coordinates. But this is kind of the origin of this formula. And now let's go on. For proving the Llarull theorem, we have to add one more ingredient to the picture that I've already shown you. So remember, G is a Riemannian metric, but now it's not really smooth anymore. It's just of Sobolev regularity W1P. And then we have the spinor bundle, and I will now concentrate on the case of even n first. The case of odd n will be discussed later. In the even dimensional case, the spinor bundle splits into two sub-bundles. That's the so-called chirality decomposition, and Clifford multiplication exchanges these two bundles. Now we have an additional coefficient bundle or twist bundle. It's just a Hermitian-Lipschitz vector bundle with a metric connection. And now I look at sections of the tensor product of these two bundles. So I do not just take sections of S as I did before, but I, in addition, take the tensor product with this kind of artificial additional bundle E. And you will see on the next slide also where this bundle comes from. And then we write down the twisted Dirac operator by exactly the same formula. So we have the, here the covariant derivative. Here we have the Clifford multiplication with the ith vector in an orthonormal frame. And so this defines a differential operator, linear differential operator of first order on the Lipschitz sections of this bundle S tensor E. So E is just a Lipschitz bundle. We can just talk about Lipschitz sections, not of smooth sections, but still it makes sense to take first derivatives here, at least almost everywhere. And so from the Lipschitz sections we get to L2 sections here, and then it turns out that this defines a densely, so this is a densely defined, essentially self-adjoint operator in the sense of functional analysis. When we take the closure of this operator, then the domain of this closure is equal to H1. functions or sections of Sobolev regularity H1 with values in L2. And as I explained before, this Clifford multiplication exchanges S plus with S minus, and this means this operator takes sections of S plus and it gives us sections in S minus and the other way around. And now, so this is classical theory. It turns out that this is a Fredholm operator. The kernel and the co-kernel are finite dimensional complex vector spaces. And the dimensions of these vector spaces can be combined in this formula. So you take the dimension of the kernel minus the dimension of the kernel of the adjoint operator, or if you wish, the dimension of the co-kernel. It's the same thing. And this number here can be calculated by the famous Atiyah-Singer index formula that still holds in this low regularity situation. So here we have the A hat genus of M, this topological invariant, and the Chern character of E. So you can think of both these expressions here as differential forms. On M, the A hat form just depends on curvature properties of G, and the Chern character involves the curvature of the bundle E with connection. So we have a good hold on this index here, and if the index is different from 0, this means that this number is different from 0, and this means then that either the kernel or the co-kernel or the kernel of D minus have to be non-trivial. And this is then how we apply this formula in our applications. Now, the Schrödinger-Lichnerowicz formula for this twisted operators takes the following form. In our situation, remember, we have our manifold M, we have our map F to the sphere, a comparison map. This is the Llarull situation. And on Sn, I can take any smooth Hermitian vector bundle, smooth bundle, and if you pull back this bundle along your comparison map F, you get a vector bundle on M, which is just a Lipschitz bundle, because F was assumed to be a Lipschitz map in our theorem. And now, as I told you before, this Chern character, this involves some curvature properties of your twist bundle. For curvature, you need second derivatives, but this is just a Lipschitz bundle, so you just can take first derivatives. But what you can do, you can compute the curvature of the original bundle E0 with the smooth, and then pull back the curvature along your Lipschitz map F. And this then gives you a bounded form of degree 2 on M with values in the endomorphisms of E. This is what I call the curvature of E. And from this, I construct a linear operator or a section, again, in the endomorphism bundle of the twisted spinor bundle using this formula. And now we write down a version of the Lichnerowicz formula, Schrödinger-Lichnerowicz formula, which is capable of incorporating the scalar curvature distribution. And for this, we integrate once, and then we pass to a distribution scalar curvature of G. And this means we get this integral Lichnerowicz formula, namely the squared of the Dirac operator, or the Dirac operator applied to a section psi, the norm squared, is equal to the sum of these three expressions. Here we have the norm squared of the covariant derivative of psi. Here the scalar curvature distribution appears. So the first two parts are like in the classical formula. And then we have a new ingredient which involves the curvature of E of our twist bundle. And now we apply this formula to prove the Llarull theorem, proof of theorem A, first steps. So this is what I want to prove. I have a spin manifold, n is even. For simplicity, I assume n is at least 4, so that I do not have to make this case distinction here. Then I have a low regularity metric, and I have the lower scalar curvature bound of G. F is my comparison map to the round sphere, and I have the two vector assumption, and the degree is, I can assume, larger than 0. Different from 0, but up to orientation, it's actually then larger than 0. And I want to prove that F is a metric isometry. Okay, let's go through and the proof here using our machinery. And then it's actually rather direct to conclude what happens here. So we have the spinor bundle on M, it's even dimensional, it splits into these two parts. The sphere is also a spin manifold, so the spinor bundle on the sphere also splits into the positive and minus part. And this means when I pull back this bundle along F, E still splits into the plus and minus part. And so that's a twist bundle over M. I get the twisted Dirac operator as I wrote down on the previous slide. And the Atiyah-Singer index formula now tells me that if you take the positive part of this twisted bundle here, which is the direct sum of the positive part, tensor positive part, and then plus negative, tensor negative, if you take the positive part and then it goes to the negative one, the index of this operator, d plus, is this number here. It's the Euler characteristic of Sn of the sphere times the degree of f. And this is a positive number. This means that since this number is positive, it's, as you recall, the index is the difference of dimensions of kernel of d plus minus kernel of d minus. If this is positive, the kernel of d plus must be non-zero, so we get an H1 section in the positive part of our twisted spinor bundle, which is non-zero and lies in the kernel of the twisted Dirac operator. This is what the index theory gives us, basically for free. So we find this section of the twisted spinor bundle. Now we plug this section into the Schrödinger-Lichnerowitsch formula and see what happens. On the left-hand side, we get 0 because this part here is 0 using this property here. And what happens on the right-hand side? We have these three summands. And the first one is non-negative. This is clear. It's larger than or equal to 0. By assumption, the scalar curvature of G is bounded below by 1/4 times n times n. So the scalar curvature is bounded below by n times n minus 1. This expression is bounded below by 1/4 n times n minus 1. And now it turns out, and this is kind of the miracle which happens here, that this remaining term is bounded below by minus 1/4 times n minus 1. So this means the sum of these two quantities here is bounded, or it's non-negative, and this means that, because here we get 0, both of these summands have to be 0. And this is a very strong conclusion. So this property here, so this is the important term here, because this involves the twist bundle E, which has to do with the comparison map F. The computation of this term here, this is the main ingredient in the Llarull paper from 1998. And so there is a proposition which says, okay, this linear operator applied to a vector, an element in this twisted spin bundle, then we pair it with omega. This is bounded below by minus 1/4 times n minus 1 times the norm of omega squared. And equality holds under very special conditions. Namely, this map, this comparison map, has to be an isometry at the point x. And we have, in addition, a condition on the Clifford multiplication. So dot means Clifford multiplication, the Clifford algebra bundle on M. And so we take the Clifford product of two orthonormal vectors in M. Then we apply the differential of F. We get two orthonormal vectors in Sn, because this is an isometry. And here we take the Clifford product in the tangent bundle of Sn. And so this element omega lives in the tensor product, and this is this tensor product here. So omega lives in the +1 eigenspace of this linear operator here. And so what can we learn from this analysis here? In our Llarull situation, we have this comparison map, and on the previous slide, we saw that this adds up to something which is non-negative. So both of these terms have to be 0. So this term here is 0 under these conditions, and this means that the differential of f is an isometry almost everywhere. And the scalar curvature has to be constant as a distribution, and the norm of psi of our spinor has also be constant. This is this condition here. So this is really little bit surprised, or rather surprising, that we have so strong conditions. And the reason is that these two terms here add up exactly to something which is non-negative. So we have the minus 1/4 here, plus 1/4 here. This is really remarkable. But that's the driving force behind this proof. Okay, and now, as I explained to you before, if f is smooth, then f is in Riemannian isometry automatically, because then f has to be a local diffeomorphism, and as n is simply connected, the covering map must be a homeomorphism or a diffeomorphism even, then it's a Riemannian isometry. But in the case of Lipschitz comparison map, this is not that easy. But let's also note this second condition here. So I repeat it here again. And it's rather interesting when you look at the paper by Llarull, then this condition here is actually more or less neglected. Llarull doesn't really use it because he need not use it. He's in the smooth situation. So he writes down such a statement here, but this property here is not really written down in a visible way. You have to study the paper a little bit more carefully to see that. But this will be the key to the solution of our problem with in the case when f is just a Lipschitz map. Okay, so the question now arises, if the differential of a map is an isometry almost everywhere, is f a metric isometry? So this is now, I would say, of general interest. So the situation is really the following one. You have two smooth manifolds, M and N. Both of them are equipped with continuous Riemannian metrics, so we can measure distances. And so then you take a Lipschitz map and assume that the differential of this map is an isometry almost everywhere. Is f a metric isometry? And to understand what's going on here, let's look at this example. You take a map from the round sphere to the round sphere, which leaves all the coordinates x1 up to xn as they are. And here with the first coordinate, the following happens. If it is negative, it stays negative. If it's positive, then it becomes negative. So this map is one Lipschitz. The differential is an isometry almost everywhere, but f is not a metric isometry. It's this map here. It's a fold map. And that's funny. So of course we see that the problematic points are this one and this one. These are the fold points. Everywhere else it is more or less a smooth isometry, but we have to deal with this problem here. So if if the differential of f is an isometry almost everywhere, unfortunately the Llarull theorem is not proven yet because of this fact here that this may happen. So the map can still be wrinkled in a completely crazy way, and we do not see what's going on. And actually this was the point where we got stuck for quite a while, until we saw that in a different area something has been proven, and it seems to be kind of well-known fact, that we can readily use to solve this problem. And this led us to write down the following theorem. Namely, as I told you before, M and N are connected oriented smooth manifolds, G and H are continuous Riemannian metrics, and you take a proper locally Lipschitz map which is pi1 surjective, or you can assume that N is simply connected if you wish. Then the following two properties are equivalent. F is a metric isometry, and the differential of F is an isometry almost everywhere. This we knew before. But the additional condition that we need is that df is orientation preserving almost everywhere as well. And this is exactly the property that fails here. So on the red part, it's not orientation preserving. Okay. Obviously, the difficult part is going from 2 to 1. Going from 1 to 2 is elementary. Going from 2 to 1 is the difficult part. And the difficult problem is proving that f is actually a homeomorphism under these conditions. Once you have this property, then you can make usual length comparison arguments to conclude that with this condition, df is an isometry almost everywhere, the length of curves is preserved and f is invertible. So then you are more or less in business, but this is the difficult part, that F is a homeomorphism. And why is that true? So the gift which we saw, or the kind of fact that it was proven in a different area, this comes from conformal geometry, and in particular from the theory of quasi-regular maps. So I looked in the book by Rickman, which was fantastic to read, and so it was very useful to us. And this actually enabled us to see that F must be at least a local homeomorphism. So let me go quickly through the definition of quasi-regular maps. It's a version of quasi-conformal maps without the condition of being a homeomorphism. So we have a map F defined on an open subset of Rn with values in Rn. We call this map K quasi-regular if it's of Sobolev regularity 1n, and it's also assumed to be continuous. And we have, in addition, this second condition here, which already appeared in some other talks during this week. Namely, this basically says that the maximal distortion, so the maximal stretch divided by the minimal stretch, is bounded above by a certain number k. So this you measure by taking the operator norm of the differential of f, and you take the nth power of it, you compare this with the determinant of the differential of f, and so you must have this inequality with some number k. It must hold almost everywhere. So that's a usual quasi-conformality condition. But there is also a second thing hidden in this formula. The right-hand side is not allowed to be negative on a subset of positive measure. So this means the determinant of the differential of f has to be non-negative almost everywhere. And this brings us to the orientability issue, actually. This is rather nice. And just get some so a glimpse what's going on here. In dimension 2, you can take any complex analytic map, even with branch points, and then always with k equal 1, these conditions are fulfilled. In higher dimensions, you can, for example, take the following map. You go from R2 to R, and the coordinate on the second factor is preserved. And on this plane part, this R2, we take a map with wraps everything around k times, where k is an integer, which can be larger than 2. So this angular coordinate in polar coordinates, it's multiplied by an integer k, wraps around, and then if you write this formula down, you see that you can work with k equal to little k squared. Interesting. So here we have branch points, and here we also have branch points, or the whole line. The z-axis consists of branch points, and but now this contrasts to this interesting, really remarkable theorem in the theory, and probably people here in the audience know it much better than I do, so I was really glad to have it here. So in all dimensions, at least 3, there is a k, a conformality factor k, larger than 1, which serves as a threshold. Whenever you have a k quasi-regular map such that k is smaller or equal to this kn, then it must be a local homeomorphism. So branch points cannot exist. So think of this k as a number which is a little bit above 1, and once you have a k quasi-regular map with this conformality factor or below, then this map must be unbranched. It is a local homeomorphism. This works in all dimensions, at least 3, because in dimension 2 we have these examples here. And this map is a branched map. So now we take this theory this theorem as a black box, and if df is orientation preserving all isometry almost everywhere, then this condition is fulfilled with k equals 1. If you pass to local coordinates, maybe with a little bit larger number than 1, but you can apply this fact here, and you see f is a local homeomorphism. And once you have this fact, then f is a metric isometry, as I've shown before. So lending this theorem from the theory of quasi-regular maps, we are done, and we can prove, or have this characterization of metric isometries. Okay, but one thing remains to be done. I have to make sure that the condition is fulfilled, that the differential of f is orientation preserving almost everywhere. And this is something that has not been discussed by Llarull or anybody before, so we have to deal with this property. And amazingly, the spinor geometry, in addition, gives us this information. The differential is orientation preserving almost everywhere, and for this we play around with chirality. This is a very important tool in the spinor geometry. So we have the plus and minus part, and so these are actually defined by the action of the volume element in the Clifford algebra, which splits the spinor bundle in the plus and minus one eigenbundles, and the same with the sphere. And since psi lives in the positive part of S tensor E, we know that the volume element of M tensor the volume element of the sphere acts as plus the identity. This is this plus here. We already knew that the psi is non-zero almost everywhere, and we have this condition, so the action on of the tensor product or the Clifford product of two orthonormal vectors. And now if you take an orthonormal frame of Tm, and you write down this formula here, then you can divide these things, you can group them in little packages of two elements, of two vectors, since the dimension is even. And so this means if you write down this whole product here, then you apply this formula here n half times and see that this element acts as plus the identity. So this is the volume element of M. This is plus or minus the volume element of the sphere, plus or minus depending on whether df is orientation preserving or not. But we know that this formula must hold. And we already know that this formula holds. And this can also only be true if this product here is plus the volume form of Sn and not minus. And therefore, this thing is plus the volume form d. So df is orientation preserving almost everywhere. So this is the additional ingredient, and for this one has to really go through the proof again and see what information we can use here. But in the end, the proof is rather short. And so this actually finishes the proof of theorem A for even n. Now, for odd n, this is the part which is more recent, and Llarull joined in. The two following problems arise. So now I have to recall where we used the property that n is even. First, we used it to get the chirality decomposition, the plus and minus part. So the index of a Dirac operator on an odd dimensional manifold is actually 0, and we don't have this plus and minus chirality game. This is one point why we always have to struggle with even odd dimensions in spin geometry. Point 1 and point 2, this trick here only works if the dimension of n is even, because then we can group these elements in little small groups of two basic or two tangent vectors each time. 2 points where the n evenness condition is used. The first point, to get a non-trivial index, this can be circumvented by the following trick, which already appeared in Llarull. Namely, we just take the product of M with S1. Seems rather easy. You take a product metric, the old metric G, you take the round metric on S1, but you stretch it by a large factor R2, which then goes to infinity in the end. Then you take the product of S with the identity, goes to Sn cross S1, and here we have some map of non-zero degree to the n plus 1 sphere, but we can write down a map H with this particular property here so that we have some control on what does this map metrically. And now if you look at the formulas very carefully and you let go R go to infinity, this enables you to construct a non-zero spinor field in the twisted spinor bundle over M on the odd-dimensional manifold. So this kind of by this bypass going to an even-dimensional manifold, here we can apply the index theory. The Euler characteristic of this sphere here is still non-zero, whereas the Euler characteristic of an odd-dimensional sphere is 0. But here it's non-zero, so we are fine. We get these non-trivial sections, and then we can go let R go to infinity, and M has the spinor field. And this allows us to prove that DF is an isometry almost everywhere, as before. This is point 1. Point 2, yeah, so this is a little bit more tricky because we have to use this property here, which really relied on the curvature of the bundle E, which we pulled back from the round sphere. And so we cannot work with such a simple trick here. What we have to do here is take a spherical suspension. This means you multiply by an interval from 0 to pi, and you take a warped product metric. You warp the original metric G by this factor here. You take the product of the map F with the identity. And here you take the warped product of the round sphere, which actually then gives you the sphere in dimension n plus 1 with north and south pole removed. This is what is written here on the right-hand side, but it's really the round sphere, whereas here it's something different. But now we have to deal with the following problem. The manifold on the left-hand side is a non-complete Riemannian manifold. So when you think of, say, M a torus, and you write down this thing here, then you have the north and the south tip, but there it's not smooth. It's something singular if you add the point. And so you have to struggle with this problem to some extent. But you can make the index theory work to deal with exactly this situation. And this was done in earlier, more classical work by Giger and Brüning-Seely. And here we have to adapt it to the situation where G is a singular metric or non-regular metric, but it still works. And then, since now we have again a map to an even-dimensional round sphere of constant curvature plus 1, exactly the same argument applies that we had here. And then we are done, and we can deal with the odd-dimensional case. So the main work here is really to develop index theory for these abstract cone operators, as we call them here. Okay, so this finishes the proof of theorem A. And when you talk about theorem A, then you also must talk about theorem B. This is theorem B. This is just this is one application of this machinery. So you think of the singular situation. It's maybe interesting to have such theorems, but here's an application that is already interesting in a purely smooth setting. Namely, take the unit ball in Rn and take any smooth Riemannian metric on this ball, which is of scalar curvature bounded below by n times n minus 1. And we, in addition, assume that the boundary is mean convex, like the boundary of a round ball. Yeah, so the mean curvature is non-negative. That's what I mean by mean convex. And now take a Lipschitz map of this manifold with boundary to the round n sphere, which is, you even can take a smooth map here. It's already interesting, but a Lipschitz map is sufficient. And we assume that the two vectors condition is fulfilled. And here, if n is equal to 2, then the map has to be Lipschitz. And here we assume that the boundary of the disk is mapped to the southern hemisphere. So the ball is wrapped around the round sphere so that the boundary goes to the southern hemisphere, and the mapping degree of these two pairs of spaces, so the boundary goes to the negative hemisphere, I have to assume that this mapping degree is non-zero, and this means that, yeah, so the map really wraps around the northern part of the sphere in a non-zero degree way. And then it holds that F actually maps the disk to the northern hemisphere. The boundary of the disk is mapped to the equator, and the map is a smooth Riemannian isometry. Yeah, so this is, since I assume G to be smooth, so then a metric isometry is a smooth Riemannian isometry. And as I said before, this is already interesting if all these data are smooth. Why? Yeah, we apply A to this artificial space, which we obtain by gluing two copies of this disk along the boundary. And when you glue this, you get along the boundary a singular locus, so the metric is no longer smooth, but the scalar curvature condition is still fulfilled in a distributional sense. And now you write down the map to the sphere, you take the map F on the first copy, and on the second copy you take also the map F, but composed with this fold map, which sends everything of the northern part to the southern part. So this is a closed manifold, and the mapping degree is non-zero, so we can apply theorem A. This map is a metric isometry, and then we are done. And under these more special conditions, if the boundary already goes to the boundary, to the equator, Sn-1, then we also can apply theorem of Lot. But here it is enough to assume that the boundary of the disk goes somewhere to the southern hemisphere. So this is then a rigidity theorem for manifolds with boundary. And so it even makes sense if you have completely smooth data here, just for the proof, you have to pass to a singular situation. And so at this point, I would like to conclude my talk. Thank you for your attention.